All right, so not many, surprising announcements. I thought I would have your algorithm choices all checked through by now, but I was bogged down by another thing, so haven't got those. But I mean, rarely do I give a whole lot of feedback there because the choices are pretty straightforward, and I should be able to knock those out this afternoon. But that's the next deliverable is then the actual proposal, which we do basically a week from Sunday. So this is, there are details online, but it's not very long. It just sort of saying, right now that you've picked your algorithm, what are you going to do to demonstrate that? So remember that the final deliverable is like a 4-page extended abstract where you're kind of presenting that algorithm to an audience that is familiar with the basic context of why and such an algorithm might be used, but is not familiar with that particular algorithm. So that abstract will sort of demonstrate the basic mechanisms of how the algorithm works and then come up with some sort of example demonstrating that. So it maybe you are optimizing some test function, and I give a bunch of test functions online, and you can actually watch traces of the algorithm as it optimizes and sort of demonstrate some feature of how it shares information among the individuals that are instantiated in the algorithm, or maybe you compare it to some benchmark, or you just sort of demonstrate some general principle of how it works, maybe benefits it has, maybe costs that it has, those sorts of things. So that's kind of and so what you're presenting in the proposal is, what is that thing that you're going to do? Is it going to be a test function? Are you going to use OpenAI Gym and have it play a game? Are you going to what is the sort of the thing that you're going to have it plug into and show that it's able to do something intelligent with that system? So that is what's due in April 13th. And again, it's not very long. And that's a group assignment. And otherwise, just the standard stuff. Muddy's Point this Sunday, the concept check for this swarm intelligence unit a week from Sunday, the mini project from the physics unit Sunday, the mini project for the swarm intelligence next Sunday. And then as just a reminder, unless I trim, and I might trim Unit 7, which is on neural networks, because it's sort of wider than the others, because there's just a lot to cover in terms of the foundations as well as up to spiking. And I might maybe cut out some of the foundations so we can focus on spiking. And if I can shrink Unit 8 or Unit 7 a little bit, then we can maybe sneak in a little bit of Unit 8. But at the moment, I'd say that Unit 8 is unlikely. So the concept check and the mini project are optional, and I've done that by increasing the drop policy from the syllabus. So the syllabus says 3 and 5, and I've increased it to 4 and 6 so that it makes effectively this mini project and concept check optional. All right, so that's the policy stuff. Any questions? Okay, so we've been, introducing swarm intelligence, which is another form of population-based optimizer, but isn't based on genetics. And so we started focusing on ant system, which is kind of the precursor to ant colony optimization. As a reminder, this is a combinatorial optimizer. So we'll walk through the graph here on the next page, but basically this was originally designed not for optimizing over smooth decision spaces, but over decision spaces where you have lots of decision variables. Each decision variable itself only takes on discrete values. The motivation are ants that are using pheromones to recruit other ants to pathways that potentially have a shorter path than other pathways. And so the idea here is that path length will be the spot where we'll insert our optimization objectives. So with genetic algorithms, it was fitness. With simulated annealing, it was energy. And so it's effectively path length for these ants. There could be other things you could imagine that they're minimizing or maximizing, but this is sort of a nice concept. It's sort of based on this fictitious idea that ants are using pheromones in order to minimize path length. It's not really what goes on with most ants, because most ants don't use pheromones for navigation. They use it for recruiting. But it's still a nice story to set up this algorithm. And this algorithm is mainly due to Marco Dorigo, who's still very active in this area, swarm intelligence. So from last time, we basically set up this story. where we have J ants, so from 1 to M are our ants, and then we have N decision variables. And so each ant has her own candidate solution. So it's her own set of those decision variables. So that's why down the left here, I've denoted these as xj1 through xjn. So it's kind of like the decision variable choice for ant J. So each decision variable has its own possible values. So this decision variable, so dimension 1 of the decision space could take on values of these discrete sets. So who knows what these values are, but it's just they come from a discrete set. Likewise, decision variable 2, it could take on another set of values. Doesn't have to be the same cardinality. And likewise, all the way up through the last one in the decision space here. So, and where I'm putting these doesn't really matter. So the idea here is that we can now view this as a choice for an ant. So we've got this ant that has her nest up here. And then she is going to a food source down here. So these are sort of anchors on this path. And so the optimization objective here is what's the shortest path to get to the food and to get back? That's the problem that these fictitious ants are solving. And so the thought here is that, well, this ant, she might choose a particular path, like maybe she decides to go to this decision variable and then this decision variable, and then, or this, I guess, this value of the decision variable, and then that eventually brings her to the food. And so she could go that way, and that path is going to have a certain length. So this whole path together is what I was calling xj, this vector. So this is her path. And then this optimization objective is kind of the path length of path xj. And so the idea here is that can we use pheromones that are laid down on these nodes uh, in order to guide a population of ants to collectively sort of share information so that over time, the paths that most ants take are going to be paths that are relatively short. And so the way that's done is by putting little concentrations of pheromones. So each node, I guess, pick a node, maybe this node here. So we can say that each node has a concentration that we'll call C. And I think the notation I used last time is going to be C. I'll do I comma D, where the I is the dimension. So this is sort of the ith dimension here. So I'll call this I. And this is the D dimension in this direction here. So I'll call this D. So every node can be indexed in where it is in this map. And so we can lay pheromones on that node. So this, at any instant of time in the algorithm, this is how much pheromone is on that particular node. So we can set up a little difference equation, a little update equation, where the concentrations get updated, where Ci comma D new, the next one, so prime, so is equal to the previous CID. And then we're going to allow the pheromones to decay. So that's going to be times 1 minus rho. And then we're also going to add contributions from each of the ants that have walked along these paths that evaluate the path length themselves, and based on that path length, lay down a certain amount of pheromone. That's one way to view this. Another way to view it is if it were in physical space and there were actually long path lengths, then you could imagine a fixed amount of pheromone would be smeared out over the longer path length, and so there would be less pheromone at any particular point. So if you're either viewing this as an ant choosing to lay down less pheromone, or you're just saying because it's a longer path length and then the same amount that the ant lays down is sort of more dilute, and so that's why that each node along the long path gets less chemical. So the way that gets summed is just the sum over all of our ants, j equal 1 to m, of their little contribution, which I can just put here as q divided by f x j, their path. So this here is the, each ant has q pheromone that gets spread out over fj path length. And then again, the goal here is to minimize our path length. So this is going to mean that nodes, let's see if I can get rid of it's down here. This is going to mean that nodes that are on long paths are going to get less pheromone laid on top of them because we'll have a longer path dividing this fixed quantity. So if I want to highlight important parameters here, hyperparameters here, maybe I'll use a different color. Here's a hyperparameter, here's a hyperparameter. Of course, the number of ants is a hyperparameter as well. So this is a decay rate, right, from black. So we have a decay rate. We have a number of ants. We have a pheromone per ant. So these are our hyperparameters. And there is some degeneracy in these hyperparameters. What I mean by that is there's, if you there's not necessarily 3 degrees of freedom here in these hyperparameters. And so there's ways, if you increase Q and decrease M, then you might have similar effects. So, there's some additional, it's not quite, it's not obvious, like there's not like an immediate degeneracy where it's like, oh, well, it's, there's some other factor, tau, which is just a product of these two, and all you really care about is tau. But it's still, there's, when you're tuning these things, you might get similar effects from tuning different variables in different directions. And so it's not completely 3 separate hyperparameters, but these are hyperparameters that you then, as the one choosing to use the ACO, have an opportunity to change. So the basic idea here, and we'll then write the recruitment down on the next page, this is just where we left off last time, is that pheromone gets deposited based on path length, and then over time it naturally decays. And that decay is going to allow for paths that are not often taken by ants, that aren't reinforced, to just stop being taken at all. And paths that frequently get followed by ants will then get reinforced. And so if we set up the recruitment so that ants are initially just going everywhere, but then over time are attracted to where the pheromone is, then the paths that have the most ants are going to be the ones that continue to get the most ants. And so you'll end up getting a number, 1 or 2 paths that are reinforced over and over through this network. Maybe there's 2 or so, not necessarily 1. but hopefully both should have a relatively short path length. In other words, a minimum or a low value of the optimization objectives. So I still haven't told you how the ants make their choices. I'll do that on the next page. But any questions about this overall setup? Yeah. Each ant has a budget of pheromone that she can leave, but then it gets smeared out over each node. And so she'll leave like Q over F pheromone on each one of these nodes. So if it's a long path, she'll leave a little pheromone on every node. Well, I mean, you could, of course, build an algorithm that's like that, where you now have for every one of your ants, you have a different amount. I don't know if that would necessarily be useful to have all of ants that are sort of stickier than other ants. So generally, we view these as homogeneous ants that just do the same thing. So this isn't a single queue across all the ants, but you could say every ant has the same amount of pheromone she can spread over her path. And so the symmetry breaking is going to happen because some ants will take longer paths than others. So the ones who take longer paths lay less pheromone on their nodes, and the ones that take shorter paths lay more pheromones on their nodes. Yeah. For a given path, do you imagine that this amount is dropped on every node in that path? Yep. Okay. So as you build up this matrix, so when you're implementing an ant colony optimization, you have to have a matrix of all these concentrations. So you've got this, it's literally a matrix, and it decays over time, and so you've got to then update that. So you got all the memory of all of these different spots. And so once you have that, then how do you decide where the next ants will go, which decides how this matrix gets updated over time. So the way that we're going to do that is by creating a little probabilistic choice that's going to look a little bit like proportionate selection. So how do ants choose? And this is for ant system and also closely related ant colony optimization. And so to generate new paths, each ant, so maybe I'll just type that, each ant chooses node, I'll say node D in layer I with probability. And so I'll write P I comma D. And then again, this is going to look a little bit like proportionate selection. So what you might expect is the concentrations. I'll just add a little scalar, but I'm just going to do, and I am making this numerator a little bit longer because I'm going to add a little bit more here. So if you're writing this down, this sort of heads up. So what you might expect is I'm just going to take the concentration at each node. And so let's say this is K equals 1, 2, and then I'm going to say capital DI. So I'm going to go back just a tick here, and I'll say that there are DI points in each layer I. So just adding that information to that. So, and I can repeat that over here, but so DI points in layer I. So we're just going to take the concentration. So you're looking at you're on layer I minus one, and you're looking down at the next layer. You're the ant, and you're looking down, and this is layer I, and you've got DI options. So you want to choose among those options, and you're smelling each one of those points to see how much pheromone is on that. What's the pheromone concentration in each one of those? So the probability of you choosing one of the points in the next layer is going to be based on a proportionate selection idea, where we're just going to take the concentration on each particular node, and we're going to divide it by the total concentration. So with this hyperparameter alpha that allows us to scale, which sort of is going to be like temperature in softmax, it allows us to sort of say, how important is it that it is the max concentration? So down here, I'll just put C, I guess it'll be I comma K. Did I do that right? Yeah, I think so. Alpha. So that right now is just saying, summing up all the concentrations scaled by hyperparameter alpha, divide the contribution of each particular one, and that gives us a distribution that we can just draw our choice from. Now, we might have prior information that suggests that certain nodes on each layer are more likely than others. And we have the ability to encode that by basically kind of like so you can imagine one way to do that would be to initialize that matrix with existing chemical on the matrix. So you sort of can say, ahead of time, before the ants even start, I'm going to pretend like ants were already there. And I think these three paths are ones that they should be more likely to choose. So I can just initialize the matrix so that those paths already are sort of reinforced, and then maybe the ants will then start taking those. But if they're really bad, then as long as some ants are going down other paths, they'll discover those and they'll reinforce those. That's one way to do that. Instead, what we're going to do is add in another set of the parameters that you would add. So I guess what, eta? I think I've got that right. NID. So these are these bias parameters that you can add. And so all of that is still under that sum. So if it helps, I can put little square brackets to make that clear. Maybe curly brackets, because I like to use square brackets for other things. Round brackets, I guess. And so these here represent prior information. So they're static, and they're provided at the start. And so this sort of biases search. So this is potentially nice or nicer than just initializing the pheromone trails. Like, I knew a guy who was sort of a famous ant biologist, and in the very morning he would like get into work at like 7 a.m. And he was one of the first ones to actually work with the guy who discovered the pheromone trails in ants. And he would get up in the morning and he would paint. He knew there's certain compounds that certain ants used to do trail laying, and it would be something to get his like mind working in the morning. He would go into the lab and he would just paint trails, and then he would just watch the ants take the trails, and it was like this therapeutic thing to as you're up in the morning at 7 in the morning, you're at work, and it sort of just got him thinking. And that's kind of like that'd be one way that you could bias the ants to say, I really want to make sure you take this path, and so I'm just going to hyper reinforce it initially. But this approach in ant colony optimization kind of goes further than that, and that this never dies away. Like if you just painted the matrix ahead of time, eventually that would get lost if the ants found something else and it got reinforced. If you really want to constantly provide them some tension, then these bias terms are always in their decision matrix. So this is really modeling not an external bias of like where the chemicals were when they got there. This is like an internal bias inside the ants where they just really are prone to pick one of these things over another. So it's almost like a memory or a fidelity that even though like this is social information and this is like private information, but because we're initializing all the ants as basically clones of each other, everybody's got the same private information. So if that's another way to think of it, you can think of this as a little bit like private inclinations within each ant. But then remember that each ant is a clone, is the same, well, I'll say clone of others. So they all have the same private inclinations. I don't want to say that we're going to add, you could add a superscript J, and you could then say, well, this ant really likes to go this way, and this ant really likes to go this way. But I would have no idea how to set those ahead of time. This at least smacks of kind of Bayesian optimization, where you have some like, I really think this is probably the best, but I want the ants to go wherever they can go, but I really feel like I want to suck them closer to this if possible. So if you can go this path, great. But if you happen to find a much, much better path, take it. But I really prefer that you go to this path. So that allows you to set up this probability. And again, I'll just mention that where alpha and beta are hyperparameters, similar to temperature in simulated annealing. I guess I'll highlight those to be consistent. And then this is sort of also a hyperparameter. So I guess I'll highlight like that. And that's how ant colony optimization operates. Is that every ant calculates this, she chooses her next node, you go to the next ant, you choose their next node, you go to the next ant, then you've got all those generations. So once everybody chooses their next node, then you do that again, and then eventually you got a round of that, and then every ant chooses their next path, and then you evaluate all the paths, so you calculate the fitness functions for every path, you then lay new pheromone according to those fitness functions, and then you start the process all over again and have the ants say, right, now that we've put new pheromone concentrations down and let them decay, then where are you going to choose now? And then you just keep letting the ants choose. And then over time, hopefully you get 1, 2, or 3 paths that are reinforced, and all the other paths kind of die out. And hopefully those paths are minimal or very small length so that they minimize your optimization objectives. So questions about that? That's the mechanism of ant colony optimization. Okay, so if I wanted to, if it helps, I could say, pseudocode, so ant system, pseudocode, basically, you've got, M population size initially, so you set that. You've got your N decision variables. That's not really a setting. You've got your DI values for each I from 1 to N decision variables. You've also, of course, got these hyperparameters, alpha, beta, rho. Am I forgetting any of them? I think that's pretty much it. So that's kind of where you start. So from that, we generate M initial solutions randomly. And this is like random search by ants. And so that just sends ants through random paths through the matrix. And then we have while not termination conditions. So as with all of these metaheuristics, termination conditions are up to you. And then we can say for I equal 1 to n, and then for k 1 to di. So now we're walking through all of the nodes of the matrix. Then we say for update. I guess I can make this. I'll make this d to match what I wrote on that first one. For d equals 1 to di. So update concentration c I comma d. That's what I used. I first. Yeah. And so this is going to make use of all of the xj's, the f optimization function, and the decay rate. So those all are engaged there. And then once you update that concentration, then we can evaluate the probability p id, which will guide how often ants then take the next path. And it's important that all of the ants sort of have the same PID, because that allows for this reinforcement and kind of coalescing on one or two paths. So all ants smell the same chemicals, the same pheromones, basically. So we evaluate that PID, and that will then take us to next D and next I. So that updates all the concentrations. So then these are the concentration updates. And then for, I think J equals 1 to n. Now we just have to update the ants. So then for I equals 1 to n, then we're going to generate new solutions. So for every ant, every candidate solution, we generate a new solution. So for every decision variable within that solution, then select value, I'll just put it here, select value based on PID. And then we go to our next I. I'll do a semicolon there to make it clear. And then that's it for the ants, then next J. So this is our update, solution updates. And then if I can do an end while, I would. So end while. And that's basically ant system right there. Oh, I had all this space down here. I didn't realize. Any questions about that? It's a cute little algorithm. Turns out for things that you think it should be good at, like traveling salesman problems, not very good at. It's at least there are plenty of other off-the-shelf algorithms out there that are really good at TSP, and it doesn't really compete very well. So, but what's nice about it, I think, is that it does have the ability to give you alternative solutions. So rather than than converging on a single good solution, then you actually do end up getting often like a couple of different solutions reinforced. And so you get one, two, maybe three solutions out. And so that can potentially be kind of nice. So I guess I'll just mention this. So ACO or AS is not very competitive in benchmarks like the traveling salesman problem. So traveling salesman's problem is just sort of finding a path that crosses all of these nodes, and only once, that is the shortest. And these are all things that sound like this should be designed perfectly to do that, and it ends up not being very strong at it. Maybe that's the reason why ants don't actually use this to optimize their routes. They use it for other reasons. They do use it, like there are ants in the tropics, for example, that actually lay their trails on tree branches. And so tree branches create a discrete network. So literally when they exit a hole in a tree, that's where they live, in trees, and their food is in a tree elsewhere. And then it really does look like this path here. They like walk out the tree and they walk down a branch, and that branch then has got branches that cross it, and then they need to choose a branch, and then they'll walk that way, and they'll walk, and so they end up having this network so across their food, so each one of these discrete choices, and they do lay down pheromone. And what they you end up finding is that you can then go, and people like Deborah Gordon have done this, you can cut those branches and then watch how they reroute their network. And this approach combined with randomness, and so if you take this approach, but then you also, so that, I guess that probability, when I say combined with randomness, if you take that probability seriously, so that you don't make it so they always take the maximum pheromone concentration, there's always some probability that they'll go the other way, then you find that they can rapidly rebuild. And so it may be that if in ants that are using this to optimize paths, it's less about, in fact, I think Deborah has shown that they don't often pick the shortest path between their nest and their food source. But the paths that they do choose have other interesting regularities, which suggest that they're more resilient to these types of things. Like if an animal goes by and bumps the tree, and then suddenly that breaks that connection between those things, then it allows them to more quickly reroute. So there's a lot of like options nearby, or it actually seems to minimize the number of nodes. And so it may be that something that was not shown in this map here, because it just doesn't quite make sense to an optimization problem, is there are going to be some paths that have different numbers of layers. So it may be, like I think Deborah's actually shown that, is that paths that tend to be selected are ones that have fewer decision points than paths with many decision points. So even when the paths with many decision points, like I hit a branch, and I'm going to take this branch, I hit a branch, I hit another one, I take that, even if that zigzag route happens to be shorter, even in total distance, the ants tend to prefer, I take this long curve over here, I turn once, and then I get to my food source. So for whatever reason, that seems to be one that their kind of ant colony optimization like trail network seems to prefer. So there may actually be engineering cases where this type of distributed intelligence can really benefit. But it doesn't appear to be the traveling salesman like sort of problems that I think it was originally intended to. Now, you don't hear about ant system, you often hear about ant colony optimization. And ant colony optimization was a modification of ant system with additional heuristics to improve performance. And these are non-ant inspired heuristics. And so these heuristics tend to make ant colony optimization far more competitive than ant system, but it's still not obviously the better choice rather than off the shelf ones. So where, so the kind of, I will say still not very strong relative to conventional discrete optimizers. So what are ACO's strengths? And I would suggest that the strengths of ACO are that, for one, you get this ability to have kind of plurality in the solution that is converged upon. So you can have not just your, like, so maybe you'll have top 2 or 3. And then the other thing is may be I'll say may inspire solutions. I'll say I'll say may inspire future metaheuristics that go beyond minimum length or minimum path length. Min path length. And I won't expand on this in writing too much because I'm not quite sure what I mean by this, but I do know that in the few cases where ants appear to do something like ant system, they aren't minimizing their path length. They're doing other things. And we're starting to learn more about the regularities and what they're doing, but we still don't know what the adaptive value of those regularities are. We can make some claims. It's about resilience and so on, and we're sort of trying to understand, how could that possibly improve resilience and so on. But once we know more about those network features, then these could be better for, let's say, topological optimization. And this is something that we haven't talked a lot about, but let's say, for example, you're talking about, normally when you talk about neural networks, that's another type of network that's out there. You talk about, I've already drawn out the architecture of the network, and now I'm just optimizing the weights on every particular link in that network. Now, there's the other question of, did I choose the right topology to begin with? And that is a much harder problem. And there are optimization metaheuristics that are designed for topological optimization. Topological optimization is not something your standard off-the-shelf, atom, stochastic gradient descent will do. I mean, all of the standard optimizers that you use, whether you're building, a giant large language model transformer or a relatively simple, binary classifier, regardless of what you're doing, those, you pretty much lay out the entire network and then you train it assuming that all of those links stay there. But this idea that there are certain topologies, now you could argue, well, what if I set a weight equal to 0? Well, that gives you a subgraph of one topology you've chosen. But if it's a qualitatively different, one that has all of these additional shortcut links and stuff like that, you're probably not going to bake those in to the latent structure that you originally give your optimizer. So this topological optimization is potentially very complex. And this is low-hanging fruit for ant-inspired algorithms, because ants aren't doing the problem that Dorigo hoped they were doing. But ants are doing topological optimization. And so if we could find a way to redesign ant calling optimization to do selection of topologies of networks as opposed to optimization of existing networks, it's my guess that ant colony optimization ant system could return as a major player in that space. But not a lot of people have done that, in part because now there's additional metaheuristics that people are using here that are kind of halfway decent, but also in part because I just don't really think people are there yet in the demand for topological optimization isn't quite there yet. They're still sort of counting on a graduate student spontaneously coming up with just like the attention paper with transformers, like they're just like somebody popping out a new, a new insight that just came out of their head, and then everybody using exactly that structure for 20 years until the next, random insight comes into play. So, but eventually people might actually start wanting computers to come up with better topologies. And I think we'll start seeing a whole new type of optimization metaheuristic that maybe this will be competitive in. But for now, ACO, it's a curiosity, but when I do like simulation optimization, I rarely go to ACO. GAs and PSO, which we'll talk about here, this unit, I tend to be a little bit stronger, even though they're not designed for discrete optimization. And so there are other choices, and there's a bunch of discrete optimizers that aren't metaheuristics that actually have provable, bounds on their performance and things like that that you could use instead. All right, so any questions about ant colony optimization before we move on to BFO? Yep. So they add a lot of sort of global information. So there's additional broadcasts of, and I'd have to look back, but you could imagine that, if you notice certain phenomena. So basically what they watch ant system work, and they notice it would get into these traps. And so then they added these heuristics to say, like, well, if we know that we're getting into these kind of failure modes of ant system where they're getting kind of stuck at these bad solutions, is there any way we can detect that and kind of reset the ants so that we can sort of say, hey, all of you ants, go do something else? And that's why it sort of adds this kind of supervisory node, that is not, I mean, that's not what the queen is doing. So it's this weird ant overlord that gives them sort of that massages their information that gets them out of these weak spots. Yeah. Other questions? All right. So I segue from ant optimization to another metaheuristic that is close to my own academic history. Was actually developed by my advisor. That is not, super popular, but it's popular enough that I think I can present it without just it seeming like a nepotism sort of thing. But I present it here because it's a chemical inspired recruitment mechanism for optimization that I think actually does have, better performance. And this is bacterial foraging optimization. Or BFO. And this is due to Passano, who was a control theorist. All right, so bacterial foraging optimization it's inspired by these flagellated bacteria that have the ability to run and tumble. So basically, these little flagella so there's this little bacteria, and they've got all these flagella that come out one end of them. So these are flagella. And if they rotate in one direction, they create a thrust that pushes the bacteria straight in one direction. But if they rotate the other direction, they get into all of these tangles that cause the bacteria to rotate in place in a random orientation. So these two modes, so I guess I'll just write these down. So if they do flagella are counterclockwise, rotation, then you have a so-called run. And if the flagella are clockwise rotation, then you have a so-called tumble. And so this creates these trajectories where you see a bacteria that will sort of have you move straight and then it'll suddenly stop, and then it'll move straight for a while, it'll stop, move straight for a while, it'll stop, and so on. So you get these kind of run lengths. So this is sort of a sample trajectory. And so you get kind of an average run length um, from each one of these runs. All right, so that's the picture. These little bacteria are going around. And it turns out that when they do the tumble is non-random. So points of tumble are non-random. And so they appear to be triggered by changes in nutrient, and I'll say and other chemical for now. Well, this is kind of a foreshadowing, triggered by changes in nutrient composition or nutrient concentration. So basically, what happens is this bacteria will, it looks like they tend to run, and the tumbles tend to be correlated with where the nutrient concentration has gone down in the gradient. So while they're moving up a gradient, while the nutrients are flat or getting higher, they move in one direction. But when it falls off, when suddenly they hit the edge of a nutrient distribution, then they tend to tumble and then they move randomly again. So I guess I can say that here just to make it clear is that tumbles happen at nutrient drops in concentration. And this tends to, for a single bacteria, allow them to move up gradient. So if these are all moving in this direction, it tends to move up gradients. And so this is kind of cool. What's also sort of interesting here, and I haven't looked into this enough to really know that what I'm saying is actually true, but the folk knowledge here is that the length scale of the bacteria is so small relative to the changes in the concentration that are detectable in medium that it's impossible for a bacterium to like measure. Like you might say, well, how does the bacterium know that the nutrient has just decreased in this direction? Well, if I put a sensor at my toes and a sensor at my head, similar to having two eyes or two ears, I might know that the nutrient concentration in my head is lower than the nutrient concentration in my toes. And so across my body, I might know whether I'm going up a gradient or down a gradient. And if that were the case, then in one shot, I take these two measurements and then I know, do I keep running or I tumble? But supposedly, these bacteria are so small that there is not enough information at the length scale of their own body lengths, their own cell lengths, to be able to do that. That suggests that in order for them to detect these nutrient concentrations being declining, there is a type of memory process within the bacteria that is able to keep track of where their most recent concentration, whether it's high or low, relative to the current. So these little cells, individual cells, are doing a kind of a little bit of a calculation there, and that might be what's determining what's doing each one of these tumbles. So, but the point here is that however they do it, they have these random turns which allow them to climb these nutrient gradients. Now that means that if you mimicked an individual bacterium, it would be pretty good at finding local optima. You just drop it in a little pit of local optima, then it should be able to climb that nutrient gradient and find the point where you're highest on those nutrients. But then it would get stuck there. So it doesn't look like it'd be particularly good at searching the whole space. But it turns out that bacteria do appear to be good at searching the whole space. And so how are they doing that? So before we go into that, how, any questions about this so far? Single bacteria, how they climb gradients just using run and tumble. And I hope that so where we're going with this is what we will be simulating a population of bacteria whose movements will be kind of like movements in a little bit, I guess the closest thing we have so far for me to describe to you is a little bit like simulated annealing, where we're going to have movements through decision space, where they'll be able to walk through the decision space, trying new candidate solutions. And then at a particular point, they'll make a turn and then they'll walk in a different direction through the decision space. And that's how each one of the bacteria will generate new solutions. And we are going to couple those bacteria together in a way that is akin to how the ants got coupled together. And that will allow them to not only do local search, but to do global search. Yeah. That's what we're about to get to. That's this hint of and other chemicals. Okay. So this, I guess, the hint here is that, I'll just put it up here, individuals are good at local search, but may get stuck at local optima. Now, a notable exception to this, there is a bacterium, there's a set of bacterium that not only, well, they move in a different way. So they're not these like flagellated bacteria that are swimming. They actually kind of can send out kind of a little anchor and then pull themselves. And so then they kind of move this way. And sometimes those, interestingly enough, will actually they'll backtrack. So what I mean by that is they'll be moving in this direction, and then they'll just randomly shoot kind of a foot out the other way and then pull themselves back. And so there have been some mathematicians that model these particular bacteria and show that, and you can empirically show this too, that when they get stuck in like spatial corners, like so the nutrient gradient is really high in that corner, but there's maybe a better gradient way over there, but they might get stuck in that corner because they just keep driving towards it and they just get stuck, like they just physically can't go anywhere. But after they get stuck there for enough time, they start backtracking, and then after a certain amount of backtracking, then they kind of turn on their optimizer again. And that tends to help them get out of these local traps. So it's a little bit like, spontaneous tumbling that isn't triggered by a tick down in the nutrient gradient. So, but in this simple description that I've given you so far, I hope it's clear that they're good at local search, but potentially bad at global search. Turns out that bacteria communicate. So they send lots of chemical communication. One famous example is quorum sensing and autoinducers. And so there's a bunch of bacterial phenomena, like the plaque on your teeth. That's a bacterial biofilm. It is bacteria turn on the ability to create this plaque, and that but they have to determine when to do that. If there's enough bacteria around and they all turn that on, then you get this nice biofilm that benefits, it's kind of sort of this public good that benefits all of those bacteria. But if you start putting out, trying to build one of these biofilms without anyone else around, you actually you aren't very effective at building the biofilm, and you make yourself more likely to be cleared by the immune system or be noticed. And so bacteria tend to want to keep it on the down low until there's enough bacteria around. And so they emit these autoinducers that some bacteria, they respond positive to them, sometimes they respond negatively to them, but there are a bunch of bacteria that use them to detect whether enough bacteria are around. And when there are enough bacteria around, then they flip on to a different behavior that allows them to do things like, become very virulent. And so this becomes like, you might have a low level of bacteria in your system, but once they reach a critical amount, then they turn this thing on, and then suddenly you got all this gunk in your lungs because the bacteria have realized there's enough bacteria that they can actually produce this gunk, and the immune system can't clear it. So that's kind of where quorum sensing is. The other cool thing about quorum sensing is it creates spatial patterns. And so you can have bacteria that are in a kind of a clump in a fluid with a lot of liquid going by, and the liquid that goes by will flush out these autoinducers. And so the ones that are underneath other bacteria will be flooded with autoinducers. The ones on the edge will not get any. Well, what do? The ones on the edge that get a low level of these autoinducers, they then start forming a biofilm that protects the clump from the liquid flowing by. So you get this little cyst where underneath the cyst is a bunch of bacteria that know that they're safe because they're getting all these autoinducers from all these other bacteria, but the ones on the edge that know that they're unsafe are generating this good that's protecting the group. So they can coordinate in all sorts of really interesting ways using this chemical communication. And they have all sorts of different types of signals. There are now researchers out there that instead of culturing, like right now, if you think you have a bacterial infection, they'll take a swab, they'll put it on a plate, they'll sit it in an incubator for a week, and then they'll call you in the results where they take it out, they see if anything's grown. And that, so they have to wait for enough bacteria for them to actually see the bacteria. But there are now people that are using mass spec and other sorts of analytical chemistry devices to look for the communication between bacteria instead of the bacteria itself. Because then you can actually detect bacteria at lower levels before they've really turned on their big growth mode. So there's a lot of chemical communication going on in bacteria. It may not be as conspicuous as an ant trail, but it is just as coordinating as an ant trail. It's doing the exact same things. So, so that sort of suggests that there could be social solutions to bacterial foraging that escape from local traps. And so what we're going to do is modify our description of the individual so they pay attention not only to a nutrient composition, like the food that they're looking for, but they also pay attention to the concentration of chemicals emitted by other bacteria. And they make their tumble decision based on a balance between those two things. And if you're familiar with training neural networks, this is going to look a little bit like when you create a loss function, you've got kind of your error term, but you might also have a little regularizer that sort of shapes the way in which the optimizer's working. And that's largely what this chemical communication is going to do, is that it will sort of be like you've got private information about the optimization objective, but then you've got public information about where everyone else is searching. And then those two things together will kind of come into balance. On top of that, we're also going to have clearing results where if you haven't been very successful for that long, you die and new bacteria are born. And that's going to allow for innovation to occur. So there's a bunch of different mechanisms here. As we present them, I hope you'll see that that they're inspired behind the scenes by simulated annealing, by genetic algorithms, by ant colony optimization. There's a bunch of bioinspiration here, which is hidden behind just the facade of it's all about bacteria. But there clearly are relationships to other metaheuristics that we've talked about so far. All right, so the social solution, so we're going to introduce a population of bacteria. So I'll just mention that we have a population of bacteria, and we're going to have elimination and dispersal. Elimination, so this is supposed to be a with, elimination and dispersal. And so this here is a little bit like the GA. So I've mentioned that some of this, so we'll see hints of SA, GA, PSO, or ACO in bacterial foraging optimization. Okay, so let's try to get into some details here. All right. So the basic structure. Let's just start this out and we can wrap it up next time. We have, in fact, let me see how far do I want to go here? All right, I guess I'm just going to sort of make a hint here and then we'll pick up next time so that we're going to have a population of bacteria with positions in decision space. And we're going to have that each bacteria senses fitness and concentration of chemicals from others. We also are going to have each bacteria emits chemicals that decay with distance. And then we're going to have movement rules based on this combined information. And then elimination of poor performing bacteria. So these are the elements that we're going to formalize starting next time. We're going to say, here's what the sort of spatial distribution of the chemicals look like. This is going to end up being a very complex simulation of bacterial behavior that is computationally costly, but it is highly accurate. It gets out of local traps, and it actually can even deal with dynamic optimization objectives. And so that's the speed accuracy trade-off. You make a very, very accurate high fidelity sim. Takes a long time to use as an optimizer, but it's actually a pretty good optimizer if you've got the computational budget. All right, that's all I got for you. So we will see you on Thursday. Happy April Fools.